Hello, everyone. My name is Cyrus Rupa. I will be presenting about the Autonomous Systems Hub along with Sagar today. I'm also co-op at the Ideas Clinic, and we've been working on creating some electric vehicles this term. So a little background. We've seen a recent trend with electric vehicles, IoT, and autonomous driving becoming extremely popular in industry, and with that, we'd like to create labs where students are able to be exposed to such things. So for that reason, the Ideas Clinic has been working on creating a suite of vehicles ranging all the way from a 1/10 scale car, which you can see on the left, to a go-kart, which a person could sit in. That's in development to hopefully be completed by the end of this term as well, all the way to an electrified Porsche 914. This is Professor Beatty's personal fun project, and it is also extremely fun. I've been working on it this term as well. The main focus over this term has really been on the 1/10 scale car. A reason for this is that students will be able to learn about a lot of the things that go on with electric vehicles and autonomous vehicles in the lab. So we can see here on the left, this is the first version of the autonomous car. This is basically just a regular Traxxas remote control car that you could buy for your child for Christmas. However, Sagar has made some very special modifications to it. On the top here, we can see that there's an NVIDIA Jetson Nano. This is the real brains of the operation and receives all the inputs and makes the decisions for how the car drives. We then have a USB hub, which just serves as an interface, and we have some sensors on board. This round sensor up here is called a LiDAR. The way LiDAR works is it just shoots out a light beam and it takes the time for the light to come back. And by knowing that, we know the distance of how far away objects are. It works the very same way that sonar does, and it's also, We then also have a stereo camera here. This camera is an orbit camera, and it allows the computer to actually see what's going on in front of it. This is the same technology that's used in Teslas, and it actually can pick up and use AI to determine people walking and various obstructions in the way. Thirdly, there's also an inertial measurement unit, or an IMU. What this does is it can monitor accelerations and changes in steering. So as the vehicle actually moves around in 3D space, it can report back. On the right, we see we've got a hardware diagram. So the way that this works is we have all three sensors, which can feed out a lot of raw data, and that makes it somewhat convoluted to understand sometimes. So we do something called sensor fusion, where we combine all of the data into a simple package for the computer to handle. That data is then sent to the NVIDIA Jetson Nano here, which is in the middle of the frame. And that allows it then to use various softwares to control exactly where it's going, how fast it's going, and what it's doing. The Jetson Nano will also output data logging features, which allow students to view what their code actually did in the real world once it ran, and we can see if the AI or if the camera was picking up the right things and things like that. Furthermore, then power and signal is sent down to the Arduino drive unit. On the newer versions, we have an Arduino drive unit with a motor shield. This controls the steering of the car as well as driving power for all four motors in the vehicle. There are two power systems on board. One runs at 5 volts and one at 7.4 volts. 7.4 volt system is used for the Arduino drive unit and to power the motors, and there's a 5 volt system on board for all the sensors and computers. The reason for the two different systems is that in the event of some sort of short circuiting, we would not damage any of the sensors or computers as they are more costly. We can see here the version 2. We've gone to acrylic, and this is for a number of reasons, the main reason being the single process manufacturing. If a professor wishes for their students to actually design a whole new car to learn about chassis dynamics, steering dynamics, and suspension geometry, this is a great way for them to do it, as it's easy to laser cut parts out of acrylic, and they go together and have a very decent strength. Additionally, we can see here on the right the new CAD model that is in the works of being built. These vehicles will use 4 motors and a belt drive system, and the beauty of this is that we can switch the gears around, which you can see here in gold and gray, or you can put in all new gears if you'd like, if a professor values a higher torque application at a lower speed or a higher speed with a lower torque. Additionally, as you can see, we have lots of mounting holes around, and this again just allows for further adjustability of the car. And with that, I'll pass it on to Sagar to talk about the software side.
Thanks, Cyrus. So Cyrus outlined the physical car, the physical hardware, which is a very important part of this project. But with the onset of the pandemic, we had to get kind of creative and find ways to allow students to work on this project from home. And regardless, we don't want students in the lab 24/7. So to do this, we created simulation models of all the sensors, the physical car, and the world or environment. So in the left half of the outline screen capture, we see the simulated stereo camera, LiDAR, and other sensors. On the right-hand side, we see the simulated world. So now you'll see the car driving forward, the sensors updating in real time, giving students nice visual feedback on what their program is doing. And once they've kind of tested their code in simulation, they can bring it to the lab and test it on a real car. So with this architecture, we've kind of tried to make it modular and allow for students and instructors to decouple the different simulation models and choose which ones they want to use for their particular course or project. And the simulation runs on the Microsoft Azure cloud, so that is very nice as well. Students don't necessarily need to install anything on their computer. And so I'd like to give a special shout out to Stephen W. for spending a lot of time on that Azure Cloud Simulator. So we already have buy-in from one professor, Nasser Azad, who's teaching a systems design controls course. So he came to us kind of with a very specific goal of using this vehicle simulation, but allowing students to be able to write their code in MATLAB and Simulink. So systems design students are very familiar with MATLAB and Simulink from first year. So with the help of Moise, another co-op student, we were able to quickly modify parts of our simulation to allow for interfacing with MATLAB and Simulink. Now students can write their code in a familiar language, deploy it on the simulator, and also interface with the real car. And so this course is scheduled for winter 2021, and we're very excited to get this project kind of in the hands of the undergraduate students. Finally, another direction that we're looking into and actively developing now is an end-to-end deep learning-based driving model. So we all know deep learning and AI are important, and we hear about these concepts every day. But in fact, these concepts are used in real autonomous vehicles. So to better equip our undergraduate students with the skills to attain careers in this field, we're trying to come up with a nice deep learning activity for them to do. So this initiative actually garnered the attention of Microsoft, and they've become a partner with us and actually made us a test site for one of their latest AI products that is yet to hit mass market. So we hope to work with them and bring their know-how and cutting-edge technology into this project and into the undergraduate curriculum. And that wraps up the summary of the Autonomous Systems Hub. To end off, we'd like to highlight the support of Wattcar and Avril. Specifically, Chris Shum has provided a lot of support and mentorship to our team, and we appreciate his role in shaping this project. So thank you for your time.
Thank you.